Yeah, thank you very much. My name is Paul Szabo. I'm a researcher at the Space Sciences Lab of UC Berkeley, and I want to give an update on our simulations of sputtering of the surface and specifically looking at the effects of granular porous regolith that we have on top of the lunar surface. Now, we care about sputtering of the moon from multiple points of view. On one hand, the moon is continuously bombarded by solar wind ions, as Anastasis discussed before. This is mostly hydrogen, but also helium. And they erode the lunar surface on an atomic level, and this can contribute a high energy component to the exosphere that allows remote observations of the surface composition, but also processes that affect the surface. And this knowledge is important for the moon, but is also very applicable for other planetary bodies, such as Mercury or moons of Jupiter, for example. Now, there is also an interesting aspect regarding the volatile balance about the ion radiation, because hydrogen, solar wind hydrogen, can be implanted and contribute to the hydroxylation of the lunar surface. But sputtering as a result of ion impacts can also remove volatiles from the surface. And therefore, we require a good understanding of how the sputtering process actually works to see how the volatile balance is affected by this process. Now, generally, to understand sputtering of the moon, there's essentially two pieces to this puzzle. On one hand, we need to have a good idea of the interatomic interaction, essentially what is sketched here on the left, where you have an incident ion impacting the surface, depositing its energy in a region close to the surface. For the solar wind ions, it is mostly tens of nanometers or so. And this forms a collision cascade that ultimately results in the sputtering of atoms from the surface. Now, we can, for example, do lab experiments of the sputtering to better understand this. This was, for example, part of my PhD thesis, where you can see here one plot for the sputter yield over angle of incidence in respect to the surface normal. And we compared experiments to models with SD-TRIM-SP, Monte Carlo code for sputtering, and found that if you fine-tune some parameters, you can actually get a very good agreement, for example. However, some of those lab experiments, or most of the lab experiments, come with limitations in the sense that it is very difficult to fully reproduce all of the surface features that make up the lunar regolith. And a very important one is the regolith structure, in the sense that we have a stacking of grains that form the porous upper layer of the lunar regolith. And this can affect the ion surface interaction through local incidence angles that will severely change how much is sputtered locally. You can have possible shadowing of certain elements, and very important also, the redeposition of sputtered atoms from one grain at another grain's surface. Now, my research, or our research recently, has focused on modeling all these effects. And as a baseline, we take advantage of another process at first that also creates secondary particles, and it is included in the left sketch here, namely the reflection of solar wind hydrogen. Because we know from spacecraft observations that about 10 to 20% of the impacting solar wind protons are scattered out of the surface as a result of this collision cascade interaction and emitted from the moon in the form of neutral hydrogen. And this is an advantage for us because the hydrogen backscattering, or this reflection, allows us to observe the ion surface interaction. And by modeling this process, we have a method of verifying our models of the regolith structure and how it interacts with the solar wind ions that we can then also apply for better sputter modeling. Now, we have used the SD-TRIM-SP 3D code, which is a Monte Carlo simulation program that essentially tracks the path of an ion through a solid and calculates a large sequence of interatomic collisions, assuming just binary collisions. So in contrast to MD, what we heard before, not all of the atoms are tracked at the same time, but at the high energies at which the solar wind impacts, this is a decent approximation and makes the simulation run much faster. We use regolith setups as stacked spherical, or a stacking of spherical grains, as for example shown here on the right for one setup, including a high porosity of around 85% that we need to explain the reflection observations of the solar wind. Generally, the reflection signatures are then quite well reproduced with these simulations. You can see, for example, here how the orange simulation results coincide quite well with the gray observations of ibex from the solar wind scattering for the scattering probability, again, between 10 and 20%, like I mentioned before. One thing that also stands out as for the reflection that is an important result of the regolith, of the porous regolith, is that if you look at the incident directions coming on from the right and between 60 and 75 degrees here, most of the hydrogen is actually scattered back into the direction where they came from, not specularly forward scattered. And if we include the regolith geometry in our simulations here in orange, this is very nicely reproduced and is one of the key results of or key effects for the regolith. Now we are using this reflection verified model to also calculate sputtering, as I mentioned before, because in the agreement with the backscattering, this gives us additional confidence in our modeling of sputter yields. Now going for the sputter results, we essentially see very similar behaviors in the angular emission. You can see in this example, when ions impact under 60 degrees, so the surface normal from the right, you get a broad emission of sputtered atoms, but you get the significant second peak back around the incident direction. And as I showed on the previous slide, this is something that we similarly observe in the hydrogen reflection, which makes sense because both of these features are a result of the solar wind interacting with the same regolith section. And it can generally be understood from a geometric point of view, where we sketch here impact points of solar wind ions that just mostly preferably impact on the sun-facing side of the regolith. And from those, it is easier to emit back into the sunward direction. So we get this additional sunward contribution also for the sputtering that contributes to the exosphere and kind of alters how the exosphere gets populated from sputtering as a result of the interaction with the porous regolith. Now for absolute sputter yields, they're generally not too much altered. It's a result of interaction with increased sputtering, but also this redeposition. And we plot here sputter yields over solar wind velocity. And there is, for most of the solar wind velocities, also not too much variation, except for 200 kilometers per second or below, which is very low for what we expect just the undisturbed solar wind to have. Thank you. But this could affect magnetized regions, for example. I also talked a lot about the backscattering, and as I mentioned, there's a lot of the effects that work in the same manner. But here in the solar wind velocity dependence, there are key differences that have to be kept in mind. Another interesting aspect, specifically for the exosphere populations, are the energies of sputtered atoms. And there are several ongoing studies on deriving like physically informed models to derive surface binding energies, for example, by Morrissey et al. Or by Yegi et al. And in relation to those studies, it doesn't seem that the regolith makes much of a difference. If we compare here flat surface in blue and regolith in orange, the spectra of energies of sputtered atoms is essentially the same. Now, to summarize my presentation, we are working on modeling the sputtering of the lunar regolith, specifically accounting for the 3D structure of the porous regolith grain stacking. And we find significant effects of the regolith geometry, especially in the distribution angles or the emission angles of the sputtered atoms. So there is a significant alteration of how the exosphere gets populated by the fact that we have a porous regolith. And as I mentioned multiple times, there's generally a lot that we can learn about how the sputtering works from the observations of backscattering, but some key physical differences, such as the solar wind velocity, should be accounted for when comparing these two effects. With this, I thank you very much for your attention, and I'm happy to answer any questions.